Thank you, Renata, and thanks to the organizers for the kind invitation to speak here at Itzykson conference. And I have at least one person in the audience who is not yet asleep. So this is joint work I want to talk about today with Pierre and a number of senior collaborators and PhD students and postdocs over the last years. So I'm really a physicist, so which means I'm looking at experimental systems and I want to build the most beautiful theory, in this case a field theory, for these systems. But here I brought you a movie of my experimental system. And the system is as follows. You have a container with a liquid, in this case it's isobutanol, and then you have a wafer of silicon on which you have deposited randomly the islands of silicon. And then you push the wafer into the liquid. And that's what you see, that's a movie. So you see that the contact line, that's a line where air, the liquid, and the plate meet, is pinned due to the disorder, these islands of silicon, sitting on my wafer when I push it in. And then all of a sudden, there are jumps. Some small jumps you see all the time, and from time to time, there's a real big jump. So I want to make a field theory for this phenomenon. There's another experiment, and if you're lucky you can even hear it, which is a fracture experiment. So what you have is you have two plates of plexiglass, you sandblast them, you put them together and you sinter them, so that that they become transparent again, and then you break them like this. And that's what you see here. So this part is transparent and this is broken, and you have a front here. And here you hear the noise of the system, which is the released energy, and the amplitude is plotted. So the phonology is as follows. The plate is pushed into the liquid. The interface is stuck, the contact line. So I have regions where this drifts down with a constant slope, and then I have small and big jumps. This is a big jump, and here I have some small jumps. And I want to give you, for instance, the distribution of these jump sizes. One of these jumps I call an avalanche. Now, what is the model I want to look at? And I mean, many models have been cooked up in the community. Usually they are rather complicated. I know that on a complicated model I can never make an analytical progress, so I take the really simplest model you can think of. So the simplest model, well, apart from the disorder, is a free theory. Here, u of x is this height field. And there are two terms. Let's first look at this term. This is, well, what particle physicists call a mass term. But you see it's displaced by a value w. W would be the center of mass position of my interface, which I push into the liquid. Here you are in the co-moving frame. So W is my external control parameter. And what is m squared? Well, for the contact line experiment, m squared is the inverse capillary length. Surface tension and gravity give you a scale, which is a capillary length. That's a length at which distortions you make on the boundary decay into the. It's a scale in which you can move up the boundary and in which it decays in the body for the zero mode when I lift up the boundary. I also have energy for distortions, and the energy is in Fourier space u tilde of k, and it's Fourier transform of u of x squared. And usually you're used to free theories where free field theories where there's a k square. For this experiment, it's more or less like k. That comes from the fact that I have to integrate out the modes inside in the bulk. So I have to find the minimum energy configuration of the surface given the boundary in the bulk, and this reduces the elastic energy from k squared to k. But everything I will tell you today doesn't really depend on this. I mean, qualitatively it does not, quantitatively it does. So you can think of k square here. And then I have this order. For this order I said I put random islands of C line here. So I have a potential V which depends on x and u of x. So it's just a two-dimensional coordinate system here in my plane. And this potential is a random potential. I will take it as a Gaussian with a mean 0 and given correlations. So that's the problem I want to solve. The problem has been treated since long time, and there were beautiful mathematical techniques which go under the name of dimensional reduction. There are supersymmetric techniques which lead to a phenomenon called dimensional reduction, which turns out to be physically wrong. And so I won't go into this, just for those of you who know these techniques. The method which has proven to be the most powerful, and my talk is about explaining why it is so powerful, is the functionalization group. Here I've written the Hamiltonian replicated. If you're not familiar with replicas, just think of the following. I want to, you can think of the replicas at different times in my experiment. So I have an elastic energy, these two terms. This was my repelling potential, and well, k square here, for instance. And then I have the disorder. So if I have my manifold in disorder, I have and I average over the disorder, where I will always generate some effective attraction between configurations. Just by the fact that if I average over configurations where I have energy minima and energy maxima, well, the interface likes to go into the energy minima, so it induces some correlations or attraction between my interface. This is this last term here. Now, we learned from Wilson and Wegner that you have to do a renormalization group, and the renormalization group actually tells you how the effective potential, this is here the disorder, the correlator, will change under renormalization. And I mentioned these old names because in this work already the notion of a functional RG is present, even though afterwards when we went to these very beautiful methods of field theory, we realized that there are certain eigen functions of this renormalization group, and I don't have to look at functional renormalization. I can just live with renormalization with single renormalization constant. For instance, here if you put phi 4 of u here, you see that this term here, which is a one-loop contribution, will give you phi square square. So this would reproduce the standard RG equation for phi 4 theory. Here it's for the disordered system. So there are two terms which come from rescaling. It's a 4 minus d expansion, which is this epsilon parameter here. So this function r is a dimension. Then I have a dimension of the field, the zeta, which also appears here. And these two terms come from one loop RG. The first term you would have in phi 4-like theories. The second term you have here because it's this replica theory. Now, more interesting maybe than this equation, it's a solution, and there's something very curious happening when you solve this equation. Of course, you think, well, microscopic disorder, it's probably some smooth function, which I have plotted here, and I've plotted you the force correlator. Remember, R was the potential correlator, but my arguments are easier to do on the force correlator. So here's the force correlator, and this is what I put at the microscopic level. And then I run my renormalization group, and after some finite renormalization group time, when I reach a certain scale, which is a Larkin length, it's actually a length where metastability can appear. So when I can't decide locally on the minima, but I have to look globally, while under these conditions, my function develops a cusp. And this at the first sight looks very bad, because when I have a cusp, I have a curvature which is infinity, and the curvature I can think of as one of my coupling constants, which has run to infinity, and standard RG folklore demands that I have no coupling constant which has run to infinity, so I should better stop and go home and let me sleep. I spent a couple of years trying to understand why this method, which worked very well for instance, for the critical exponents, which are eigenvalues of this equation. So why this method worked well? So let me explain, first of all, why you need a cusp. There is no way around the cusp, and this is the basic physics of the system. And actually it's a physics, and this cusp is the key ingredient which will allow me later to do the avalanche, to treat avalanches. So here I have a random potential, and I have my external potential, m square u minus w. So the w is an external point, and this m square is just a spring. Now I look for the minimum energy configuration. And you see that while I move this green point around here, well, the yellow point will sit here, and my effective minimum energy will just be given by this spring constant, and will have a form like this. But when I move from left of the origin to the right of the origin, well, I find another minimum. So my minimum energy configuration will change abruptly. And my effective potential, which is now the spring elastic energy around this point here, will give me this next part of the parabola. So this is my effective potential, and you see cusps, but this is not yet the cusps I'm after. First I have to calculate the force. So take one derivative, so the force jumps, and then I have a linear regime here. Now if I average this, I claim that I get a cusp function. How can I see this? So let's look at the difference in force squared and the correlator. What will be the dominant contribution to this term? Well, the dominant contribution for a small window of w, so this is now the distance w, and I have a small window here. Well, the dominant contribution will come from these jumps. So this will be given by the probability to find a jump, which is density of jumps times the size of my window w times the expectation value of these jumps squared, what I've written here. And you see this function is linear in w. It's linear in w because the probability that I have a jump inside a window of size w is just linear in w. So this explains the linear cusp. Now this is and you also see how you can measure this object, because I gave you some function Rg, a function and a flow, but the question is of course what physical observable is behind this. you see a force due to this equation, due to Newton, force is actio equals reactio. So the extension of the spring constant is the force from the disorder. So if I want to measure this, and its correlation function, I just have to measure the deviations from the center of mass of my particle position. And this gives me this effective disorder correlator, which looks like the picture I had on the first slide. This you can also do in the field theory. It's Pierre Lussac who has recognized this as the first. I won't bother you with that. Let me show you some simulations and experimental results. So there are several universality classes hidden behind this functional G equation I had on the first slide. And it depends on which are the microscopic initial conditions. You can have a disorder, which is a random potential. This is called the random bond universality class. It goes in random magnets, which are also realizations of these systems. Breaking a bond is effectively random potential. So if you have this, then the fixed point function in one loop order is this dashed line here. And the green dots, including almost invisible error bars, are the simulations of Alan Middleton, looking at this simple observable, so the fluctuations of the center of mass, the correlation function of the center of mass fluctuations. Now there's a different universality class when the disorder is stronger, which is known as random field disorder. So when the random fields are short-ranged, random bond, there is a random potential which is short-ranged. And it leads to a different function, also universal, which is this blue curve here. And again in green, with the squares, here is a numerical estimation of Alan Middleton. So this is for a static disorder. I've cheated you a little bit, or I have been imprecise, because the arguments I made now were for the minimum energy configuration. But you can just repeat everything I said for the following state when you have your interface in the parabolic potential, and then you slowly move the minima of the parabola. Now, instead of looking for the global minima, whenever your configuration becomes unstable, you jump into the next minimum. And the arguments for the cusp I gave you are unchanged. What changes is that the random bond class disappears and you're always in the random field class. And the fixed point function here measured in a numerical simulation by Alberto Rosso is slightly different. Well, what I've shown here is the two-loop corrections. There is a theory for the statics and for the dynamics, and you see that simulations can pick up on this small difference. Actually, the roughness exponents are quite different. For the one-dimensional string in random field disorder minimum at equilibrium, the roughness exponent is 1, whereas for the different case, it's 1.25. Now, physics is an experimental science, so I should analyze the experiment of which I showed you the movie in my second transparency. And this is what was measured. There's an actually even better experimental system, hydrogen on a rough cesium substrate. It's better for the simple reason because the disorder is smaller and the capillary length is almost the same for all materials you can find. So you have the RG equation has longer time to work. So you will be closer to the fixed point. Well, and again, you see with slightly larger error bars than in the numerical simulations, this fixed point, this renormalization toward fixed point function measured in the experiment. Now, let's go make the transition to avalanches. And let's look again what happens if you have one avalanche. So when you move your parabola from W to W prime, on average, the interface will move from UW to UW prime. So the same distance, because it is confined in this parabolic potential. It can't go far. This object here, I can decompose exactly as the probability to have an avalanche, which is the product of these two terms times the size of an avalanche. The same I can do for the second moment, for this object here. If I have only one avalanche in my interval between W and W prime, well, then this is given by this term. I wrote it approximately here because it's only valid if I have exactly one avalanche in my interval, whereas this is an exact relation. On the other hand, this function here I can expand in Taylor, and it's just the derivative of my disorder correlator at the cusp, well, times W minus W prime, which tells me that the slope of my disorder correlator, just divide the second by the first equation, gives me the second moment of avalanche sizes divided by the first one, factor of 2. So it sets me the characteristic scale of avalanches. Now avalanches, as we understand, I repeat, it's a strong response of a system when I increase adiabatically or infinitesimally some external field. Avalanches appear in a gigantic amount of systems. I will talk about the maybe oldest avalanche process I came about, the Galton process. The Galton process, we will see, is equivalent to some mean field version, also known under the name ABBM model, which was the first quantitative model to model avalanches in random magnets. We generalized this to the random force model, which is the starting point for a correct field theoretical expansion for short-range disorder. And it appears in other systems, self-organized critical systems, for instance. Now let's look at the Galton process. And Galton in 1873 asked for his time, most important question: how is my name, Galton, going to survive in time? Knowing that I have children, well, I have sons, the daughters don't count in this game. I have sons, and the sons will propagate my name. So at a given time, well, you should read this drawing starting here. I'm the first Galton, so I will have children, and the number of my sons or grandsons is living grandchildren, living descendants, is plotted to the bottom, and this object will make a random walk. So sometimes my sons have many children, and then many sons, and so on. But it can happen that they only have daughters, or they don't have children at all, and my line will die out. So this is a random walk, and this is kind of an avalanche process. Actually, this process is well known. It's a first return of a random walk in front of an absorbing boundary, and we know that it has an exponent s to the minus 3/2. And if I have some drift, in this case drift, which brings me down, then I will also have an exponential cutoff. So this would be an example of an avalanche process. How can we see this? Well, there's another way of looking at this picture, and I can't do the construction for you, but I can give you the upshot. So suppose I have my parabola. This is the random potential I see, and I've already subtracted, the random force I see, and I've already subtracted W. So if I move my parabola from W to W prime, the new configuration I can find the following way. I start at W and just go over until I hit this curve. So you can think of shining light, and only the lighted configurations can be seen. The dark configurations will never be visited. So when I move my parabola over here, I will have this very big avalanche, and evidently it has the same distribution as the times of die-off of Watson's name. Now this was for static observables and the integrated observables in time, so the total size of the avalanche. I can also look at dynamical objects. So I can ask, well, what is the number of offsprings for Watson, number of offsprings at a given time before extinction in avalanche? What would be the velocity of my avalanche as a function of time? Of course, it will be a random process, so only average quantities can be studied analytically, and here it's average shape, and it's for the Watson process, it's a parabola. So I can also ask for duration, and I can ask for avalanche size, which is the area under this curve. Now there is three levels of models and abstraction I want you to walk through. The first is a particle. You have written the equation of motion where I've taken an additional time derivative. So it's a overdamped Langevin equation. I take one time derivative. So the time derivative of the velocity is m squared times the velocity with which I move my parabola minus the velocity plus the time derivative of the force. Now, in this simplest model, the force is a random walk. So forces increase linearly, or force squared differences increase linearly with distance. Now, if I write this as a process in time, I can model this in the following way. I take a white noise in time, not in space, but I multiply it with a square root of u dot. This is possible if and only if my movement is only forward. If the movement is backward, these considerations won't work. And even for the system I showed you in the movie, and in the beginning there's a theorem, well, at least for theoretical versions I showed you, there's a theorem which ensures that movement is only forward. It's a Middleton theorem. Now this is a model of a point particle, and has been very successful in treating mean field magnets, special class of magnets, but it's of course not a model for an extended elastic object. But you can easily promote it to such a model by adding plenty of degrees of freedom. So for each x, labeling my interface, I put a coordinate u and the velocity u dot. Then I couple them with elastic springs. So I get this Laplacian u dot term in addition. And still, forces make random walks. This is a Brownian force model, and this is a model we can solve analytically. And then you want, of course, to treat short-range disorder, because this is what is relevant for experiments. And it was my former PhD student, Alexander Dubrinevsky, who realized that you can easily implement this here by just adding this additional term. It's a damping term for the force. If you do this, then the force correlator will be given by an exponentially decaying function. Now we walk you through these different models. The first model I said was the ABBM model, named after Alessandro Beatrice Bertotti and Montorso. A particle which is disorder, which is disorder forces, which are itself a random walk. And this is a model which can be solved to a large degree analytically. For instance, you get avalanche size distributions which go like s to the minus 3/2. This is exactly the same process as the golden process I was talking before. Duration distributions, which goes like t to the minus 2. Velocity distributions, which if you drive very slowly go like 1 over u dot. And you get the average shape at given duration. You can also get the average shape at given size, and it's given by this function here. Now the second model was the Brownian force model, where you take plenty of points which are elastically coupled, and each of them sees a force which is a random walk. And we have been able to show the following two theorems for this model. But first of all, if you're only interested in observables, in the observable which is the center of mass, then this is the same stochastic process as the ABBM model. And this is important to understand why this model was so successful in analyzing experimental data, because it's the same random process as this extended model which we introduced here. And the second theorem is that the field theory of this process, you can write down the field theory, is the sum of all tree diagrams. This already tells me, well, in an epsilon expansion, I first have the trees, I have to resum the trees. So this looks like the mean field version. And then I can add in a control epsilon expansion the loops. And the loops will appear when I treat short range disorder. And this is a last step in the process where what I already said this when I add this additional damping term, my equation of motion. And when I go to the u coordinate for the force, I see that it satisfies this equation, so that the correlator is given by this. So this is a disorder which is microscopically rough. So in the experiments, I would probably have disorder which is microscopically smooth. But since the physics is universal, I don't expect it to matter. So since you're all theorists, let me give you a tiny little bit of field theory. Here I wrote down the equation of motion of the position of the interface. It's overdamped Langevin equation. So the coordinate u will move in a damped way due to the forces which are on the right hand side, so elastic forces, forces from the parabola, plus forces from the disorder. Now take a derivative of this equation, and then you want to construct the Martin-Sicher-Rose-Janssen de Dominicis action, which is a fancy word for saying that I write a delta function for each degree of freedom. So I write e to the u tilde, which is a purely imaginary field, times the equation of motion for the time derivative here. You see, you recognize the first couple of elements here. Well, and then I have u tilde times the time derivative of the force. If I average over the forces, I will have the force-force correlator, which is written here. I still have the time derivatives here. And well, for later purposes, I already added a source term here, which will allow me to generate observables. Now, what is the beautiful thing about this expression here is that apparently this is a very non-local and difficult to treat action. It depends on t and t prime. But now the physics of the cusp comes to my rescue. Let's take these two time derivatives explicitly. And remember, this is my cusp function. So I take the first derivative, well, I get the inner derivative times the derivative of this function here, which is now at short small arguments is like it's a sine function. So in the second step, when I do this derivative, I have to derive the sine functions times the value of the derivative, the numerical value. But deriving a sine function gives me a delta function. So these two derivatives of my cusp function, they just produce a delta derivative at 0. And it produced me a local action. And moreover, this local action is linear in u dot. It's linear in u dot with all of the other terms I had up there. So it already tells me what I should do to sum all the tree diagrams. I mean, tree diagrams with this cubic vertex here. I should look at instantons, which I obtain when I vary this equation with respect to u dot. So to solve the instant, I have to find the instanton equation. I have to solve it. And since this is linear in u dot, the instanton equation is exact. So the instanton equation is this one here. And if I do the algebra, it's written in the next line. And just to show you how simple it is to get to the velocity distribution, I've done the calculation here for you. So I take a source, which is, I want the center of mass velocity, so my source will not depend on x, and I want it at a given time, so it's a delta function of time. When I put all these constants to 0, my instanton equation is this, and has this solution here. Now the generating function, so this is the expectation value of e to the lambda u dot. I have to subtract the one here. It's just given by the integral of my instanton solution. Well, and I can do this integral, I find logarithm minus the log of 1 minus lambda. And if I do the inverse Laplace transform, I get my velocity distribution function, which I already had on one of the previous slides. It's a velocity distribution function of the ABBM model. And I can, with these methods, calculate higher correlation functions, 2-point functions. Okay. Now, there are a bunch of scaling laws I can try to look at and test. Scaling laws can be derived. Here, for instance, as an example, you see velocity distribution function, which I derived for the ABBM model. So if I multiply with the velocity, which is the constant here, and actually the exponent changes sign. This is the scaling law and the RG calculation, and this is numerical simulations which converge for larger and larger systems finally to this value. We can also calculate the shape. It's a slightly complicated function. Let me just show you one example, maybe from an experiment. This is a Barkhausen noise data. And this is a shape at fixed duration, mean field, one loop. And you can see here as in a log-log plot, for instance, the power law in the beginning changes in very good agreement with theory. The tail changes in good agreement with theory. There are a lot of comparisons you can do. So it's a quantitative theory. I want to conclude by the relation to stochastic sandpile models, the Manner model. People in this audience, they like exact solvable models, and the abelian sandpile model is one of those. So when you have 4 grains on the side, you topple them to your neighbors. The Manner model is a variant. If you have 2 or more sides, you topple them, you move them to randomly chosen neighbors. It can actually even be the same neighbor. Now you can construct field theory out of this for the density of doubly or higher occupied sites, and for the number for the average density. Well, when you have a higher occupied sites, and you have a large density of them, of course you will have more topplings, and topplings reduce the number of these sites. So this will decrease, but on the other hand, if you land on a site where there is already somebody, this object will increase again. This will also lead to diffusion, and you have a noise which is proportional to your activity. On the other hand, the number of grains is conserved and only diffuses with the same term here. I have added some dissipation by hand. It's not in the Manner model for purposes which will become clear on the next slide. Because I want to map this model on disordered elastic manifolds. So I've written again these equations, and now you can do a simple change of variables. You call rho the activity, u dot, so the velocity of your interface, and this combination here you call the force, and then I can rewrite this equation of motion for the sandpile model as these equations here, which you recognize, I had them in earlier slides, as the equation of motion of an interface in a random force field, which is locally a Brownian motion, but at long distances, short range, correlated. So this is an analytic proof that disordered elastic manifolds and the Manner model are equivalent. So let me conclude. I have shown you field theory for avalanches. I have started with the ABBM model, which is a mean field model for avalanches, a model for a single degree of freedom. I've promoted it to the Brownian force model, which is a field theory, which still can be solved analytically, whose zero mode is equivalent to the ABBM model. And then I have constructed field theory for short-ranged models. I've also shown you relations to other phenomena like sandpile models. And I hope I'm on the time. Yes, perfect. And I'm happy to take your questions.
When you replace your Langevin equation by Martin et al. Field theory, don't you forget Jacobian?
It's in Ito dynamics.
Pardon?
I use Ito prescription, so it's always forward, so the Jacobian is by construction 1.
Well, that was pretty much what my question was about. Are there interesting limits when you take gravity to be very weak?
Yeah, when you take gravity weak or the surface tension low, then you reduce the effective mass of the theory. So, which means that from an experimental point of view, you have always the size of your microscopic disorder, and then the randomization group works until you hit your infrared cutoff, which is given by the capillary length, and whose dependence I just discussed. And of course, the longer the randomization group can work, the closer you get to the fixed point. The experimental problem is that all systems have capillary lengths of about 2 millimeters. And there's not much you can do, because if you increase the interaction between them, then you also make them more heavy, and then gravity will be more pertinent. So for instance, the liquid hydrogen and isobutanol, they have approximately the same capillary length. So it's not a parameter you can play around with.